Welcome to a short video on CRC errors in Nexus 9000 series switches. My name is Scott Hopman, and I'm a technical consulting engineer with Cisco's data center route and switch team. In this video, we'll discuss how to identify and trace CRC errors in your Nexus 9000 series switches. First, we'll define a CRC and how they originate. I'll share the guide that we'll be following today. We'll discuss the different switching modes and how they affect CRC frames, what actions the Nexus switch takes when a CRC frame is received, and then we'll conclude with a quick lab, demonstrating how to identify and trace these errors in your network. A CRC, or cyclical redundancy check, is a verification performed by a switch after receipt of a frame. Using an algorithm, the switch calculates the CRC for the frame and compares that to the value in the FCS, or frame check sequence field in the frame's trailer. Matching values validate that the payload in the frame has not been corrupted during transmission. If these values do not match, the check fails, and the CRC errors are noted in the switch counters. These errors are most commonly the result of a bad or failing layer 1 component in the path, such as the copper or fiber, a transceiver, or even a host network interface card. However, they can also result from the receipt of giant frames where an MTU mismatch is present in the environment. This video will loosely follow the guide available at the URL on your screen, with our lab using concepts from scenarios 1 and 2, focused largely on Nexus 9300 top-of-rack switches. Scenarios 3 and 4, involving our 9500 modular switches, will be covered in a later video. Also, while the general method of tracing CRCs can be followed on all Nexus switches, today we will focus on Nexus Cloud Scale. These switches contain the Tahoe ASIC, and some of the commands that we will use are unique to this hardware. A list of what models this includes can be found in the guide. Okay. Before jumping into our lab, let's have a brief refresher on how Cisco switches forward frames, and how this results in CRC frames propagating throughout the network. There are two potential switching modes that exist in Cisco Nexus switches: cut-through and stored forward. By default, Cisco switches operate in cut-through mode. First, let's discuss store and forward. In this mode, when a frame arrives, it is buffered until the entire frame has been read. This buffering gives the switch the opportunity to review the frame and perform the CRC check before the frame begins to forward. If the CRC check passes, the frame is forwarded. If the CRC check fails, the frame is dropped and the CRC counter on the ingress interface is incremented by 1. Because store and forward has to buffer every frame, this mode is slower. However, a switch in cut-through mode forwards frames much faster. It is able to do this because it begins to forward the frame the moment that it has processed enough of the headers to make a valid forwarding decision. In this scenario, by the time the entire frame has been read and the CRC check has been performed, the frame has already begun to be forwarded out of the egress interface and cannot be halted. The overall result is faster switching, but this does mean that CRC frames will continue to be forwarded. This method of cut-through switching is the default in Cisco Nexus switches. And while we cannot stop the CRC frame from being forwarded downstream, we can mark it, which notifies the downstream switches that the frame was already invalid when we sent it. The switch does this by rewriting the FCS field to a bitwise inverse of the current FCS field's value before the frame has finished egressing the switch. We call this action stomping. After the frame is stomped, the switch takes 3 actions. It finishes forwarding the remainder of the frame, including the now stomped FCS field. It then increments the CRC input errors on the interface that the frame arrived at, and finally, it increments a transmit error on the egress interface. The stomping of the CRC aids us when troubleshooting these errors in the network, since we can look at the ASIC counters on our device and determine if the CRCs were or were not stomped when we received them. If the CRCs were stomped, we know the frames were already corrupted when they left the previous switch. If the CRCs are not stomped, we know that the frames were valid when they left the previous switch and therefore must have been corrupted in transit between these two switches. In this way, we're able to trace and isolate the origin of the corruption. Now let's take a look at how to execute this isolation in our lab. Here's a look at our topology. We have 3 Nexus switches, 1 representing an ISP and 2 representing our environment, with a server connected to Nexus 2. Let's say our server team contacts us, complaining that they're receiving errors on server 1. To confirm this, we log into Nexus 2, where this server is connected. We look at interface Ethernet 1.3, that connects to the server, and we see output errors present. Checking the counters again, we see that these errors are in fact increasing. To help us diagnose where the errors are coming from, we can check the output of show interface counters errors non-zero. Here we see the output errors again on ETH13, but we also see that we're receiving errors on Ethernet 1.1. Checking Ethernet 1.1 directly, we see that these are CRC errors. These errors are often assumed to be originating from a bad component directly connected to Ethernet 1.1, but armed with our new understanding of stomped CRCs, we can check the ASIC counters to validate this. To do this, we'll first need to map our incoming interface to MAC index and MAC subport in the ASIC. This is easily done with show interface hardware mappings. Here we see that ETH11 maps to MAC index 24 and MAC subport 6. Let's make a note of these since we'll need these values in the next command. Next we'll take a look at the Tahoe ASIC counters with slot 1 show hardware internal TA counters ASIC 0. Slot 1 refers to the line card. Since this is a non-modular switch, we will always use slot 1 in this command. The same is true of the ASIC number. There's only one ASIC in this switch, ASIC 0. The output of this command is noisy, as it contains a wealth of information. Since we're only here to check for CRC errors, we'll pipe to narrow this down. In our output, we see a series of MAC indexes with subports. You may recognize this output from earlier in the video when we discussed stomped versus unstomped CRCs. The FCS output here shows counters for unstomped CRC errors, and below that we have our counters for stomped CRCs. Now we'll need our values from earlier. MAC index of 24 with subport 6. We find these here. Checking below, we can see our CRC errors are in fact stomped. This tells us that the previous switch identified the CRC error before sending it to us, which rules out the layer 1 between that switch and us as the origin of the error. Next we'll move to that upstream switch, Nexus 1. Here we follow the same process as before. We confirm the errors, leaving ETH11. We see that they entered the switch via ETH19. Then we check the hardware mappings. We see that ETH19 maps to a MAC index of 28 and a MAC subport of 6. Checking the ASIC counters, we see that the errors here are unstomped invalid FCS. This tells us that the upstream ISP Nexus believed these to be valid frames when they were sent. Based on this, we have isolated the issue to this link, and we now know that we need to replace either the fiber between these switches or the transceiver in one of them. One last thing to note here. In the newer Nexus codes beginning in 10.2.1, the output of show interface has been enhanced to include stomped CRC counters here, easing CRC troubleshooting by making the dive into the hardware interface mappings and ASIC counters unnecessary. This concludes our video on CRC errors and Nexus cloud scale switches. I hope you found this information helpful and wish you great success in tracing these errors in your environment.